Hello, I'm Mrs. J, and today we're going to go over a problem from section 3.4. I chose this one because we're going to look at it in each type of model, a linear, quadratic, and a power function. We're also going to use the TI-83 calculator, or if you have an 84, they work the same, which is nice. If you do not have the calculator, you can get a free 90-day trial of an online TI-84 calculator, and it's great. I used it in the spring and summer, but my 90-day trial ran out. But if you get it now, you should be able to make it through the final with it. So the calculator, I will put the link for it with these homework assignments. But using the calculator, let's look at a problem. This is data for our box office revenues in billions of dollars for movies released in selected years from 1980 to 2014. And that's our years. Find the linear, quadratic, and power model that best fits the revenue as a function of years after 1970. Since it wanted after 1970, I took each of the years and I subtracted 1970 from it. So 1980 minus 1970 gave me 10. Subtract 1970 from this one, get 15. Each one I just subtracted the 1970 to find out how many years it was. So that's how I found these. The next thing you need to do is plug it into your calculator. To plug those values into your calculator, you go under Stat, right here, and then Edit is highlighted. Now, if you have stuff in your list, you go to Clear List and hit Enter, and then whatever list you want to clear. Well, I don't want to clear 1 and 2, so I'll show you it with 3. You just hit Second and Clear List, and it will clear list 3. If you have another one, the comma, and list 4, and hit Enter, and those lists will be clear now. When I go under Stat again then and hit Edit, notice my data's there. It's in lists 1 and 2. But 3, 4, 5, those are all clear. And then you enter your data. I entered, and you could see the number better down here. 10, enter. What did I hit? Okay, no one hit. So you can see the 10, and you hit 10 and enter, and then 15 and enter, 20 and enter, 25 and enter, and I just went down. 30 and enter, 34 and enter. Next one's 35. Then you go over one to the next one, and you enter all of the Y values. Once you've entered them, you hit Second and quit. First one we want to find is linear. So we go under Stat, go over 1 to Calc, and then you want to find the linear. See, this linear has AX plus B. That's why I put AX plus B here. Now there's another one. If you go down further, that's linear. So you want to be careful. They will give you the same values, but they're switching the A and the B. A plus BX. So remember which one you're doing, so you remember if the A is your slope or your y-intercept. I like to keep A as my slope, so I'm using this one. You hit Enter. Since we're in list 1 and 2, we can just hit Enter. And there it is. And notice it reminds you AX plus B, in case you need to remember that. It's said to round 4 decimal places. So the first one, 0.255, that 9's going to round up, so 0.256. Y equals 0.256x. And then B, see if it's positive or negative. It's negative, so minus 0.0632. So we get this. The quadratic one, let me clear my screen. You go into Stat, you go over to Calc, and then see the quadratic right under the linear. And we hit Enter. And notice it's ax squared plus bx plus c. So our first one, which also you want to be careful because of the 10 to the negative 4. So it was 2.4923538. We're going to have to move over 4. So it's 0.0002 x squared because it said to go 4 decimal places. B is plus 0.2421x, and then plus, running out of room, 0.0985. 0985. I'll make this a little clearer once we get the other one first. Clear the screen. To find the power function, go back into Stat, over to Calc, and keep going down, you'll find the power. It says power. There it is, power. So this one will be e to a power. This is actually x to a power. So power, you want this one. And hit Enter, Enter again to run it. And there it is. Notice it says ax to the b power. So our a 0.2722 x, and then our exponent 0.9797. There we go, that looks better. So our linear would be this one. Our quadratic would be this one. I moved the decimal, so 0.002 x squared plus 0.2421x plus, and then the constant, I didn't want to squeeze it in there. And then the power function. What do all these mean? Now this one's pretty close, all three of them. And if we would look at the R value, it tells you how close you are. So this one was 0.9886. I didn't look at the other ones here. Let me do them real quick and we'll find out what they were. Linear was 9859. And quadratic only gave R squared. So if we take the square root of it, 9859. So it was just as good as the linear, but this one was a little more accurate. But they're all really strong because remember, the closer you are to 1, the stronger the relationship, or the more on the line it is. To see how close, when you want to graph your data, we already have it in L1 and L2. you want to go to stat first. Make sure this one is on, because this is the one that's going to plot the points. This one makes like bars. This one makes the dots that you want. So you want to make sure it's on and the other are off. And then you want to go to your window right there and make sure your data fits it. My numbers went from 10 to 44, so I went from 9 to 50. I probably could have went a little less and done 45, but make sure you go at least 1 unit. So we could go 45. The Y values go from 2.8 to 10.4, so we could have went from 2 to 11. And then when you hit graph, there's your points. And that's why it's kind of bending a little bit. So that's how it fits the ones that bend, but the linear, it also fits because it's almost a straight line. Now if you want to see each of them, if we click on Y, you type in your equations, which I already typed in the equations. So I'm going to highlight the linear one, 0.2560x minus 0.0632. I'm going to highlight my equal sign, so then it will graph this one. When you hit graph, and there's your line. If I go back into Y equals and I unhighlight that one and I go down, I already typed in the quadratic x squared one. So I'm going to hit enter. So now notice it's highlighted. Hit graph. And there it is. See, it bends a little bit. You can see a little bit of a bend right in here. And the other one. So if I get rid of this highlight and go down to the next one, this one's the power function. Hit graph. And there's the other one. They all look very similar because we're so spread out and stretching it. Let's check something. If we went -1 to 60 and -1 to 25. And then we'll graph all 3 lines, see if we can see a difference there. So there's our dots. That's a straight line. Oh, they're all going pretty darn close. Yep. So at this point here, they all have a very similar growth, and that's why these are so strong. It says, what do the models estimate as the revenue in 2020? So if we wanted the revenue in 2020, we would still first take 2020 and subtract 1970, because remember, X is the number of years after 1970. So 2020 minus 1970, which I know already is 50. We need to plug in 50. Now, since we already put these into graph, there's a table that will find the value for you. You hit second and table. And see how it has X1, X2, and then we'll go over and do X3. We can put 50 in here and hit enter. So when you plug in 50, the linear tells you 12.74. This one tells you 12.70. And the last one, go over one more. So Y3. tells you 12.57. So they're all close values. And that our value told us they would be close. So this one says after 50 years it would be 12.74 billion. I think it was in billions, yeah. Billions of dollars. Using the quadratic, 12.7 billion. And using the power function, 12.57 billion. So you can tell, let's find one where it's more different. Do one more. We'll just do one that you plug in. Does it appear to have a linear model? Okay, let's try this one. So the first thing I want to do is go in and clear my data. So I go stat down to clear and hit enter. And then I need to clear list 1, comma, and second list 2. Because this says list 1 and list 2. And then I hit enter and it's clear. So when I go back in there under edit, they're clear. So then I enter my data. 1, 5, 7, and 9. Or sorry, 3, 5, 7, and 9. 3, 5, 7, 9. Go over to the other side. 4.7. Why it's so dark? There we go. 4.7, 8.6, 13, and 17. Second and quit. Now I'm going to go into Y and clear these. So then I'm only plotting the points. And my window needs to go, X is 3 to 9. So I'm going to go -1 to 10. And then the other one goes up to 17. I'm going to leave the -1 so I have an axis. And I'm going to go up to 18. I'm just choosing these. So you could have went from 4 to 18. But if you use -1, it shows you the axis. But that's what they look like. It could go linear. So it says, does it appear to have a linear model or a power model? Find a power model function. Find a linear function. Okay. So it said to find the power function first. Hit stat. Go to calc. Go down to power. Right there and hit enter. Hit enter one more time to solve it. And it's very strong, 0.999. So it's one, we're only going to go 2 decimal places. 1.29, 1.29 x to the 1.18. And that's an exponent. Then it's 0.9997. Well, that would round to an 8, but let's try, so this was the power function, let's try the linear. Calc, linear, and I'm using ax plus b. We get 2.065x minus 1.565, and r is almost the same. So they are both very strong. I'm just trying to find one that wasn't. Here, look at this picture. Depending on how your data goes, this one is a quadratic and a power function. Notice that the quadratic fits it nice. This one does too, though. It's not too far off. But this one gets more of your earlier values and then not so good over here. Where this one, if you're going for future values or future years, this one looks like it starts to trend better. This one, you can see the exponential. This one, though, that line they drew is not an actual line. They're just showing you how it was growing. But having that linear in there might be better. Or a negative exponential that curves this way. But linear would probably be better for that one. If it all falls on the line, then that would be, your R would be kind of like the one we had just saw with all the 9s. Yeah, these ones, you need more data to really see the difference between them. You can see how this one, a linear, would not fit as well if we put a linear in here as if we went with an exponential or a quadratic. It would fit a lot better. This is a good one to see the difference. Okay, but if you have any questions, let me know.